Okay, and let's start our class today. And I have started talk about chapter 9, serial correlation, and which is the important parts or starting points of the time series data. Okay, you all know the difference between the time series data and cross-sectional data, right? For time series data, the order of the observation is very important. So you are not able to move the position of the original time series data, okay? And on the other hand, if it is cross-sectional data, the order makes no difference. And the order in time series data matters, okay? So, and we have talked about what's the nature of the problem, means why, what's the problem to have the most important questions in time series data is the serial correlations, because the dependent variable usually is the events to affect the y variable. It doesn't just stop at the same time. It usually it will extend it several periods. So the current periods will be affected by the previous one, okay, or previous several periods, okay. So this is what we say the serial correlation. And do we talk about the consequences? I think maybe not yet, okay? So the consequences is the second issues we need to learn if we have the serial correlations, okay? And again, I think when we talk about multicollinearity, or we talk about heteroscedasticity, usually we talk about the consequences of the problem. So again, in serial correlations, we also need to talk about the consequences of the problem. When we say the consequences of the problem, usually is talking about the estimation problems using OLS. Okay, so the consequences of the serial correlation, according to what we have on our textbook, maybe you can refer to 9.3, the consequences of serial correlation. The first one is talk about the OLS estimation is unbiased. Again, we wanted to tell you that unbiased means the expected value of the estimation is equal to the population parameters. So in other words, the expected value of the oldest beta, I mean the coefficient of the regression model, the beta is still unbiased. But with serial correlation problem exists in the model, and it really, the variation is really big. So the overestimate or an underestimate will be canceled out. Therefore, the expected coefficient is still the same as the parameters. So the variation is big. Doesn't mean that, it's not correct, but it doesn't guarantee the correctness of the beta, but it is unbiased. Okay, and the second problems is we talk about the variation, right? So if it is the variation is big. Okay, we talk about the three important properties of OLS estimation. One is unbiased, the other one is called efficient, and the third one is consistent. Okay, then efficiency is talking about the variation of the standard error. Okay, and if we have zero correlations, then the variance will usually is big. And also, if we have the problem with zero correlation, using OL as estimation, the standard error usually is underestimated. When we say underestimated, means the standard error is smaller than we expected. Okay? And if it is smaller than expected, means what? Means the t-value is larger. I mean, in absolute value sense. Okay? It is larger. If t-value is larger, means what? Means the probability is smaller. So when the probability is smaller, means what? It's easy to reject the null hypothesis. In other words, when we say it's easily to reject the null hypothesis, then we will say that the alternative hypothesis is true. And alternative hypothesis true means that the beta coefficient is significant. So in other words, in that sense, since the beta is the coefficient of the independent variables, therefore, if we say the coefficient is significant, means the importance of the x variables is more than we expected. Okay? So this is the problem. This is another consequences of the zero correlation. And then after that, we say the t-values, so the hypothesis is not reliable, right? Okay, so again, I like to say that what is the zero correlation? Means that if we have the model, something like this one, beta k xk, and this is the error terms, right? And for our classical linear model assumption, the UT is normal distribution with mean 0, and the standard deviation is sigma square. Okay, this is classical linear models assumption. But if this is a zero correlation, means what? Means UT is not like this. Okay? Maybe UT will be like UT minus 1 plus VT. And now VT is like this, but UT is something like this. So in other words, UT is serial correlations, the current periods and the previous one. Or maybe even, rho to the Q, T minus Q plus VT. Something like this one. So means the current error terms is affected by the previous P periods, Q periods. Okay? So in other words, in this case, violate the assumption of classical model, linear model. This is what we say, zero correlations. Okay, so if you have this in your mind, then I think it's easy to catch the idea we want to talk about. So zero correlations is about the error terms. Okay, this is the same as what we did in chapter 10. Chapter 10 is called heteroscedasticity. it is also the arrow terms, but that is essentially for cross-sectional data, and this issue is essentially for time series data. Okay. All right. Notice all these consequences. Then the next issue we want to talk about is how do we diagnose the serial correlations problem. Okay, I think this is something pretty new for our business students. Okay, and so I like to talk about more about how to detect the serial correlations. Okay, and we have two popular methods. One is called Durbin-Watson test. The other one is called Lagrange multiplier test. Okay, refer to our textbook. This is in chapter 9.4. Okay, and what's the Durbin-Watson test? Okay, if I'd like all of you to download the data set, which is in our e-learning system, class e-learning system, and the data set is called CHIC 9. Okay, in chapters 9, and the data set CHICK, CHIC. Using that example, then I will show how to detect whether the model has serial correlation or not. Okay, and you all have that data? And the variable definition refers to the book on page 306. And let me also say something about this one. If you're not really that possible to get the definitions, let me explain it. Okay? You all have the data now? You all have the data with you? Yeah, okay. All right, let me see. And the variable y, okay, y is per capita chicken consumption in pounds in year T. Okay, so this is per capita. When we say per capita, you can consider it as an average. Okay, average chicken consumption in pounds in year T. And PC is the price of chicken. Okay, and PB is the price of beef. Okay, YD is the U.S. per capita disposal income in $100. Okay, it means that the consumption of the chicken will be affected by its own price. And this is called demand and supply effects, right? So we call it price effects. Okay, then the substitute, which here using beef. Okay, so the price of the beef, the effect of the price of beef is what we call substitute effect. Okay, then YD is what we call income effect. Okay, so this is very typical economic models, and then what do you expect the relationship of individual variables? the PC will be negative, right? The coefficient of PC will be negative. The coefficient of the PB substitution effect will be positive, right? Because the price of the beef go up. Then the chicken of consumption will go up, right? Because, the substitution effect, the beef, the price go up, we won't buy beef. Then we'll buy chicken more, okay? Then the YD is disposable income. If you have more income, then the consumption of chicken is getting bigger, so it's positive. So we will expect the negative from the PC, positive from PB and the YD. Okay, so let's run this model together, okay? PC, PB, and YD. Open as an equation. Okay. All right. So we all have that. Do we have the signs which we expected? Yes, right? Then how about the significance of each individual x variable? It's also significant, right? Okay? All right? And now, let's see the output here. Durbin-Watson statistics. Did you see that? Durbin-Watson statistics. Okay, this is what we say, Durbin-Watson test. Okay? At the same time, I like all of you run the Gradle too. Okay, the reason you will see the reason immediately. Okay, would you please also using the data to run the Gradle? Hey, by the way, do we? Let's see. I can also download the Excel chicks to and make sure I will save that Excel file to the most updated one. Okay, then I can import it into my Gradle. Okay. So that's in English. Yes. Okay. Then I'll pull this in. Okay. Do you want to give the date time series? Okay. If you here since we starting to talk about time series data, so from now on, if you import data which is time series, you need to hit the yes here in order to invoke all the time series function from Gradle. So this is just for Gradle, okay? So here you hit yes, and this is time series data. Then it is annually. Just say yes, forward, and apply. Then you have all the time series data. Some of the, if you don't do this way, some of the time series data will not invoke from the system. You are not able to do that functions. Okay, so this is important step to use the Gradle and also use some functions from time series model. Okay, so you can run this one too. So ordinary list square y as a y dependent variable, then PC PB YD. Yes, and hit OK. So let's see these two output, one from Gradle, one from one from eViews. Okay, you will see exactly the same answers. Okay, and look at this Durbin-Watson here and the Durbin-Watson here. Okay, then what's the Durbin-Watson statistic? How does Durbin-Watson statistic will show the symptom of the serial correlation? Okay, let's see. Okay. First of all, let's understand the Durbin-Watson test. Okay, if you use Durbin-Watson test, there's three requirements or three assumptions you have to meet. Okay, the first one is the regression model includes intercept terms. Usually we do have intercept terms in our regression model, so this one is really, not big deal. The second one is serial correlation is first order. Okay, you all remember what do we mean by first order? This is what we say first order. This is first order. Means that the current residual or error terms is affected by only the previous one periods. Okay? So Durbin-Watson is only applied to the regression models which has first order serial correlations. Okay, so this is very rigid assumption. The third one is the regression model does not include a lagged dependent variable. So if you have the model, which this is what we say model, what do you mean by lagged? Lagged dependent variable. In other words, if you have the original model which says, where's my, is this the one? If you have the model like this one, and say the other one is gamma, okay, which is y minus 1 plus ut. If you have this one, this means the lag periods of the dependent variable. Lag dependent variable. Okay, I think this is the model which we haven't seen it before, but it happens. It happens in time series data models. Okay, so if you have the model with this one, okay, do not use Durbin-Watson test. So Durbin-Watson test, you need to meet these three requirements. Okay, first one, intercept terms. Second one, first order serial correlation. The third one, without lagged dependent variable. And in this model, we just say really meets these requirements. So we can use Durbin-Watson test. And what's the idea of Durbin-Watson test? Okay, let's see. How do we calculate the Durbin-Watson statistic? Okay, although you don't have to calculate it. Okay, let's see the definition of the Durbin-Watson statistic. Okay, look at this one. Okay, this is a fraction. The first one is what we call numerator. The second one is denominator. Okay, this means if you run the data, this is all called residuals. Okay, the denominator is individual residual square terms, okay, from 1 to t. Understand this definition, okay? And what is the numerator? This means the current one minus the previous one. Okay, so thinking about the current and the previous one. So what's the role? What's the role in this situation? We say that rho usually is between +1 and -1, right? This one, rho, I mean the correlation, serial correlation coefficient is between +1 and -1. Okay, so that's thinking about very extreme situation. If it is equal to 1, what do you mean by this is equal to 1? Means the current is exactly the same as the previous one with some random errors. Okay, so means the current one and the previous one is very close. In that case, if this one is close to this one, what do we mean by these numbers? The numerator is you sum all of the observations from period 1 to t, means very, very small, right? Very small, very close to 0. If it is exactly the same, means the sum of them is equal to 0, right? Understand what I'm saying here? So if the numerator equal to 0, then the d is equal to 0. I say this is very extreme case. Okay? All right? And the other extreme case is -1. If this one is negative, means the current is exactly the same values exactly, except the sign is different. So make it, the numerator will be the double of the original ET, right? Does that make sense? If this is, for example, if this is 1, this is 1. If this is 1, means the subtraction of these 2 will be 0, right? If this is -1, the subtraction will become 2. Right? So it's double of original one. So when this is double, then take the square, then square it, means 4 times. Okay? So I take this two extreme case. Means what? Means the d can be pretty close to 0 or close to 4. Then what is the d equal to 2? D equal to 2 means this is 0, right? No correlation. Then this 2 will be this one. This is 0, right? Okay, so this one will be close to 2. I mean, you can thinking about, in the mathematically, I can prove that equal to 2. But, intuitively thinking, is in the middle parts of 0 and 4. Okay? All right? So, if you have the Durbin-Walton statistics, which is pretty close to 2, means no serial correlations, right? If it is close to 0 or even less, is in the 0 side, means positive serial correlations. If it is close to, move to the 4 side, it is negative serial correlation. Does that make sense? So I think mathematically we don't have to prove those things, but intuitively we can understand the concept or the math behind. Okay? So in this class we don't do any mathematically proof, but we will intuitively explain the meaning of those math. I think this is very important for those who, it's application. Okay? All right. So, although we do have some, since this is a formal test, okay? This is a formal test, so we can have some procedures to do this formal serial autocorrelation test, okay? So, but we don't have to calculate it with this computer's output. We don't have to calculate these numbers using our data ourselves. Okay, the computer do this for us. And make sure that, here we have t-1. So if you have the data, okay, for example, you have 100 observations, then since we need to use t-1, so if you just have 100, you need to sacrifice one observation. Okay? Since we need to use t-1. Okay? All right? And after you understand this one, let's come back to our example. The eViews tell us that this number is 0.99299. So what's this number close to? We have 0, 4, and 2 in the middle parts, right? And now this number is 0.99 something. So it's moved to the 0 directions, right? And which means positive zero correlations, suspected positive zero correlation. Okay? Then we say that we have 0, like this parts. The 4 number, I should show you that. 0, this is 4, this is 2, right? So in this parts, this is the extremely case. So this is positive serial correlations. And this is negative, right? Negative zero correlation. This is no zero correlation. Now we have the number moved to these parts. Yeah, that's why I'm saying positive. Didn't I say positive?
Oh, you say suspect.
Yeah, I'm suspect positive zero correlation. Just suspect because I didn't really check it. If this is suspect, means what? What do you mean suspect? I mean, it is a highly possibility there's a positive zero correlations. So I do have some official numbers to show that it is positive zero correlations. Okay, that's why I'm saying suspected.
I mean the number between 2 and 0.
Because 0.99 is really point to these parts.
Yeah, isn't that means it's not suspected?
Well, I need to show what is exactly, right? I need to show you. I haven't shown you. So with these numbers, it's really highly possible to have positive zero correlation, right? So let me show you, okay? All right? And with eViews, you need to go back to the tables of Durbin-Watson test. Okay, let's see. From our textbook, they do have Durbin-Watson test. Okay, check with the tables, which is at the back of our textbook with table B-4. You all see that? You all see that table? Do you see that table? No. Okay. Look at this one. Table. Look at the tables. Okay? How do we use this table? Did you see K? Did you see each column with K, right? K means how many X variables. Then how many do we have? How many K do we have? We have 3 variables, right? Okay, so look at K equal to 3. And did you see that DL and DU? U means upper critical value, and D means lower critical value. Okay, and what's the N? N is our observations. So how many observations do we have? 29. Okay, look at the N equal to 29, then K equal to 3, and 1.20 and 1.65. Did you see this range? Okay, so our number is 0.99, means what? Even lower than the lower critical value. In other words, it is significant. So this means the critical values to check with. Okay, so the positive 1.20, is the lower limit, and our is 0.99. Therefore, definitely by checking with these tables, we know that it is positive zero correlation. We show it. There's evidence, enough evidence to show the positive zero correlations. Okay? And I like to say that with these tables, okay, before we using T distribution, we using Z distribution, even we use F distribution, or even I think we didn't use chi-square, but actually this chi-square is one of the distribution you have to know about it. Okay? With all this test, if we refer to the table will tell us either reject or do not reject, right? But for a Durbin-Watson test from this table, if the falls between the upper and the lower, means indecisive region. So you don't know. It's not sure. It's indecisive. Indecisive means you're not able to make a decision. Okay, this is the Durbin-Watson, the one drawback of Durbin-Watson statistic. But fortunately, in ours, example 0.99, which is lower than lower limits. So it's positive zero correlations. Yeah, it's indecisive. Indecisive region. We don't know. So it's hard to make decision, right? Even you go through this official test, and the answer is I don't know. Okay, so this is the drawback of the Durbin-Watson statistic. Okay, so if you have e-views, there's in the e-views didn't show you all this test. I mean the official with the p-value or something. But if you turn on this Grados, okay, then we just run the output from the Grados, and if you go to the test using Grados, that test. Okay, did you see the Durbin-Watson p-value here? Did you see this one? Durbin-Watson p-value. Do you see that? You all see that in Gradle? Let me run this one. Okay. You can do it. No, Y. This is Y. Just you hit the Y and yeah, okay. Okay, then okay. Well, you have to have C. Yeah, sure. Constant. Yeah, do not eliminate the constant. When I do it again, it's not. Oh, here. Okay. Then run the test. Did you run the test? Choose the one. Go to the tests and Durbin-Watson p-value. You all have that? You all have that? Huh? You all have? Oh, you Python? Okay, fine. Did you get the numbers of the Durbin-Watson? Okay, let me show the result. Maybe you can check with the Pythons, okay? This. Positive autocorrelation, the p-value is so smaller one. No, this is the Durbin-Watson numbers. I mean the p-value. Here. Where's the p-value? Okay. Where's the p-value? You know, I'm glad you're using Python. You know, at the same time, you all have that? Yeah, that's right. Okay. You all have that. So this is the, you know, by checking with table, I just using 1.20 as a critical value, but I don't have p-value, right? Okay? And in Gradles, they tell me the p-value. So definitely, with this p-value, I will reject the null hypothesis. And there's enough evidence to show the positive zero correlations. Understand what I'm saying here? Any questions? 有吗？你 run output 吗？你要 run output。model 吗？这第一个。Because the computer doesn't know whether you check with the positive zero correlation or negative zero correlations. But we know that this is positive numbers, right? Our Durbin-Watson statistics positive, right? So we'll check in with this positive autocorrelations. The p-value is this numbers.
Also, if this is a negative correlation,
Yeah, that's right. Okay? Understand what I'm saying here? So Gradle give you the p-values. And eViews give you the statistic, but without any official checking numbers. But you can check with the tables using critical value approach, and Grados give you p-values. Understand what I'm saying here? This is the p-value. This one. This is Durbin-Watson statistic shows here. This is Durbin-Watson statistics using the number I just showed you, that D equal to the fractions. Yeah, this one. Okay, you don't have to calculate it by yourself. You know, the computer calculated for you. And that shows the number in the Grados as well as EViews. And EViews doesn't show any official test result, but Grados does. Okay? All right? So this is what we say, how to detect zero correlations. The first test is using Durbin-Watson statistic. But you have to meet the 3 requirements in order to use Durbin-Watson statistic. Okay? Is that clear for all of you? Okay, all this, the procedures of Durbin-Watson test is from our textbook. Okay, you can read it. Okay, am I using this example to show you how do we get these numbers from output as well as the computers? Okay, and also I explain the Durbin-Watson statistics. How does this Durbin-Watson statistics ideas coming from? Any questions so far? Did you get the numbers? Pythons. Is Dylan still in Singapore? Huh? Still in Singapore. So how long does that conference? Tomorrow. Okay. So miss the class. Okay. All right. Any questions so far about the Durbin-Watson statistic? Okay, this is what I have with my notes, that using Durbin-Watson statistics and since we know that Durbin-Watson's test has to meet these requirements, and these 3 requirements makes limitations, right? If you don't meet any of them, or either one of them, then you are not able to use the Durbin-Watson test. Then what do? If we cannot do that. Okay, there's another one which we say that the popular alternative to Durbin-Watson test is we call Lagrange multiplier test. Usually use LM to identify the Lagrange multiplier test. Okay, let's stop here for a while. I will come back after 10 minutes.